Hello, in this video we'll talk about the difference between calculus and precalculus. Basically we'll talk about two problems. The first problem is the tangent line problem, and the second one is the area problem. Okay, let's talk about the tangent line problem. We know from precalculus that if you have 2 points A and B, and we know coordinate of A, XA, YA, and here we have XB, YB, then we can find the slope of the straight line passing through A and B, right? So I write the slope is equal to YB minus YA divided by XB minus XA. That is the slope of the straight line passing through A and B. Okay. So what is the slope? I hope you still remember this. Suppose this is alpha, right? The angle. Then the slope is nothing but the tangent of alpha, right? So the tangent of alpha is equal to this distance divided by this distance. The first one is nothing but YB minus YA, and this is XB minus XA. So you have the slope, the tangent right here. This is really, interesting because we have tangent in here. And that explains why we call, some line, like tangent line, right? Okay, now let's talk about this. Suppose that you have some curve, okay, and you have A right here, you have B right here, then you connect A and B, okay. So as we have seen that we can find the slope of this straight line, okay. But I really want to find the equation of the line which is tangent to the curve at A, for example. So I want to find some tangent line right here, okay? And I really want to find the equation. In order to find the equation of some straight line, we need the slope, right? We need its slope. And now we already have one point A, so the slope is basically what we need to find, okay? But how to find the slope in this case? Imagine about that. If our point B, suppose that B is, like running, right, along the curve. And let B run, or let B approach A this way, okay? So each time when B is closer to A, so I have some second like this, right? Of course, when B runs, the angle also changes, right? And the slope also changes. But you see, when this point is approaching to A, the angle alpha also approaching to this angle, right? So the slope of the tangent line, I write here the slope of the tangent line is some limit, right? That is some limit. I write limit of what? Of this slope, the slope right here, right? When B approaches A. Does that make sense? So, basically we need to consider some limit processing here. That is what I want to say. We need to consider some limit process in order to find the slope of the tangent line. Okay, So we cannot do that in precalculus because we don't know how to do limit process, right? But in calculus, we know, and we need to do that in order to find the slope of the tangent line and then find the equation of the tangent line. Okay, so that is one thing that makes, calculus and precalculus different. But before we move to the next problem, I would like to explain a little bit more about the slope of secant AB, right? And the slope of the tangent line. So what is the difference between them again, right? Of course, I don't write any formula in here. I don't write any limit in here, right? But we know in order to find the slope of the tangent line, we need to do some limit process. And in order to find the slope of some straight line, knowing 2 points on that straight line, we just need to apply this formula, okay? All right, let's have another look at this. So if I have 2 points, right? 2 points A and B in here, and I say, yeah, I move from A to B. I move from A to B, right? What is YB minus YA over XB minus XA? What's that? Suppose that X is measured in time, right? So this is nothing but the average velocity. Is it correct? Or sometimes we say, yeah, that is the average rate of change. That's the average rate of change. That means you use this formula, right, to find the slope of the straight line passing through A and B. But, in some applications, that is the average velocity of the movement from A to B, or that is the average rate of change. Because on the top, you can see the change in Y, right, divided by the change in X. So that is the rate of change. Makes sense? And that is the average rate of change. Okay, now let's involve limits in here, right? Now I want to consider the case when B approaches A, okay? So I can write the following formula. All right, I have limit of YB minus YA over XB minus XA, okay? Let's say when B approaches A, right? But what does mean B approaches A? So I can write in this case just, XB approaches XA, right? Okay, and what is that? That is what we have in here. That is the curve, right? So we have tangent line here, and this is the instantaneous rate of change. Instantaneous rate of change. Oh, that's what? That is velocity, instantaneous velocity. Right? When you drive a car, the speed you see at some moment, that is instantaneous velocity, instantaneous speed. Right? But if you want to find average velocity, it's pretty easy. You just take the total. You just take the total distance you already passed, right? Divided by the total time, right? Total of time in here. So in order to find the average rate of change. But in order to find the instantaneous rate of change, we need to take the limit in here, okay? So that is another look on the difference between, the slope of some secant and the slope of the tangent line, or the average velocity, the average rate of change, and instantaneous rate of change, or instantaneous velocity. Okay, so that is the first problem. That is the tangent line problem. I repeat again, right? In precalculus, we don't know how to do with limits, but in calculus, we need to deal with limits. All right, let's move to the second problem, the area problem. In precalculus, you know how to find area of some squares, right? Or some rectangles. We know how to do that. You know, if you have x, y in here, so basically the area is equal to product of x and y. Okay? But in reality, you will see a lot of problems like this. Suppose you have some curve, right? Which is y equal to f of x. And suppose that the curve is continuous. Means, you know, we don't have any breaking point, right, on the curve. And you consider some interval a and b, and they ask you to find the area of this region. You don't have any rectangle, you don't have any square in here, right? And you have some strange figures, and they ask you to find the area of this. So how to do? You cannot use precalculus to solve this problem. Okay? But the idea is, again, we need to use the limit. Right? We need to use the limit. Let me explain that very briefly, right? So, you can imagine we want to find the area of this region. And suppose that if I connect this guy with this guy together, right, we can find the area of this trapezoid. We know, right? We know how to find the area of trapezoid. Okay, but we still can find the area. Or we say we can approximate the area of the original region using the area of trapezoid, right? Okay. Let me choose another way. I can use rectangles, right? I can use rectangles. So I may choose this way, right? Yeah, I say, yeah, I choose this rectangle. And I can approximate the area of the original region using the area of this rectangle with the left endpoint. Make sense? Of course, you know, it really depends on how we choose, right? Because you, in this case, you have a big arrow in here, right? But it is still an estimate, is that correct? With a big arrow, okay? So, at the same time, I say, yeah, I still can use, you know, the right endpoints, right? To approximate. So I can use the right endpoint here, right? But in this case, yeah, it's obvious that, you know, the estimate is bigger than the actual area. Is it correct? So it is just examples, right? That tells you that, yeah, we can use trapezoid, we can use rectangles, you know, with the left endpoint, with the right endpoint, or, you know, even you can choose, you can pick any point right here, right? You say, yeah, x0 between a and b. And then you have some f of x0 right here, right? And from here you can draw the triangle as you want. You have another estimate. Does that make sense? But again, right, that approach is about precalculus, because we know how to use those figures, right? Rectangles, trapezoid to approximate. But they ask us to find the exact area of our region. So using this approach, we cannot find the exact area of our region. We need to do some limit process. Look at this. Okay, I just want to choose one interval. I don't want to make, you know, the situation more complicated, right? Let's consider just two points in here. I have some curve, right? Let's say this is A and B, right? This is A, B, this is A, this is B. We do almost the same thing with the tangent problem, you see. I say, yeah, if I use rectangles, right, like this, and I consider some limit when B approaches A. When B approaches A, okay? So, when B approaches A, of course, the arrow in here approaches 0. Does that make sense? If you use, this rectangle. Okay? Again, right? If you don't want a left endpoint, you may choose right endpoint, right? But in this case, your arrow look like this. And of course, when B approaches A, the arrow approaches 0. When the arrow approaches 0, you get the exact area. Okay, so using this observation, we may divide the interval, the original interval A and B, into subintervals. So I can divide A and B into subintervals, right? Let's say this subinterval, subinterval, subintervals. How many we want, right? So let's say, yeah, they have the same width, okay? It's just, for easiness. And then each time I can approximate like this. Yeah, I can approximate the area of this part using the first rectangles, right? No? And then I use the second one, and then I use the third one, and then the fourth one, and so on, right? And of course, each time you see some error right here. You see right here, right here, right here, right here. But that's okay, when you consider some limit. When you increase the number of subintervals in here, right? Suppose that, in this case, we have 4, right? But you might increase to 5, 6, and so on to n, and then maybe to infinity. Don't forget that. That means the number of subintervals increase to infinity. In that case, those arrows, will approach 0. And in that case, you will get the exact area of our region. That means you need to consider some limit in here. When n approaches infinity, where n is the number of subintervals. Okay, so of course that is, we still need some other conditions, but that just helps you to understand the difference between what precalculus can do and what calculus can do. All right, so I hope that these two problems helps you to understand the difference between calculus and precalculus. And in this course, we will go over all of them, right? So a half of Calculus 1 is about tangent line problem, about the slope, about the velocity, or sometimes we call derivative, okay? And the second part of Calculus 1 is the area problem, okay? So we need to deal with integration and other things. All right, so I hope you enjoyed this video, and please let me know if you have any questions about it. Okay, see you in the next video. Thank you.